Welcome back. Today, we are unpacking something absolutely critical in the EV world. We're talking about the intense safety systems that stop an electric vehicle's battery from losing its nervous system. Because, let's be real, the communication network is literally the lifeline between the car and the internal battery pack. So we're going to explore the extreme engineering that guarantees this lifeline never, ever breaks. Let's get right into it.
All right, so let's define our ultimate villain for today, the terrifying data blind zone. This is exactly what happens when the EV's communication network completely crashes. Imagine flying down the highway, and suddenly the battery management system goes completely dark. It loses all visibility of individual cell voltages and temperatures. It's a catastrophic scenario, right? And engineers have spent thousands of hours figuring out exactly how to stop it from happening. To see exactly how they defeat this data blind spot, we'll walk through the entire engineering lifecycle. We'll start with diagnosing the root causes of COM failures, then look at the bidirectional backup architecture, DFMEA design controls, PFMEA process controls, and finally, extreme DVPNR production validation.
So, starting off with Phase 1, diagnosing the root causes of these communication failures.
We're basically looking at two completely different battlegrounds here. On one side, we have internal physical stress breaking the daisy chain. That's our U029A fault. This is a violently hostile physical environment. Constant high-frequency vibration and wild thermal expansion cause micro-metal fatigue, literally cracking solder joints. You also get micro-fretting, where pins rub together at a microscopic level, oxidizing and spiking resistance until the connection just fails. On the flip side, we have external threats, faults U0100 and U0111. Here, the enemy is completely invisible. The motor inverter is switching massive amounts of power super fast, and that unleashes brutal common-mode electromagnetic interference, or EMI, that can easily drown out normal CAN bus signals.
And here is where that invisible physical enemy gets really interesting. The network relies on two 120-ohm terminal resistors to keep a perfect 60-ohm impedance. But if one of those resistors gets knocked loose from all that vibration, the impedance instantly doubles. The communication signals hit a dead end, bounce back, and create these massive high-frequency standing waves. It violently distorts the signals, the error counter just blows past the 255 limit in a flash, and the controller is forced to shut down into a self-isolating bus-off state to stop corrupted data from spreading.
Which brings us to Phase 2, the bidirectional backup self-healing architecture. Isolating these faults instantly is kind of like solving a high-speed logic puzzle. The internal comms use a bidirectional ring topology. Normally, data just flows in one direction, but the exact millisecond a wire breaks, the system detects the drop and instantly fires data from both ends. By seeing exactly where the forward test ping stops and where the reverse ping stops, the software pinpoints the exact physical wire break dynamically. And the craziest part, it maintains 100% data transmission while doing this. The driver doesn't feel a single drop in torque. Now, to stop the algorithms from reacting to dangerous ghost data caused by those EMI bit flips we mentioned earlier, the system uses ultra-strict end-to-end security. EMI can literally flip a digital 0 to a 1 as it travels down the wire. So, by slapping an independent 4-bit rolling counter and complex CRC math checks onto every single message, the safety layer spots even a single flipped bit instantly. If the math doesn't perfectly match up, the system just tosses the message out.
But hey, if the system truly cannot heal itself, a rigid fault-tolerant time interval, or FTTI, takes over to safely kill the power within 2 seconds. It waits 500 milliseconds first, just a quick debounce window to be absolutely sure the signal isn't coming back. But the second that timer hits 0, strict safety protocols kick in. Before the 2-second mark, the BMS commands a 50% power limit, blocks fast charging, and executes a soft cutoff to safely isolate the high voltage pack without violently jerking the car. All right, moving into Phase 3. Knowing all these risks, engineers use DFMEA, Design Failure Mode and Effects Analysis, to bake prevention right into the blueprints.
You know, the AutoSAR adaptive recovery algorithm is all about balance. It desperately wants to reconnect, but it also has to protect the CPU from frying itself. When the external CAN bus crashes into that bus-off state, the software attempts a rapid recovery, trying to reboot the connection every 50 milliseconds. But if it fails 5 times in a row because of a hard physical short, it's smart enough to switch to a 2000 millisecond slow recovery mode. This stops the transceivers in the CPU from just burning up by endlessly hammering a shorted circuit.
And to physically block that electromagnetic coupling, the 3D design rules are brutal. They strictly ban parallel routing and demand a minimum 100mm air gap between the low-voltage comms and those massive high-voltage copper bus bars. Low-voltage wires act just like antennas.
If you run them right next to cables carrying hundreds of amps, the magnetic fields will absolutely obliterate your data. By forcing that physical air gap and crossing wires at angles instead of running them parallel, engineers completely cut off the interference path.
Now for Phase 4, exact process FME controls. Because designing it is one thing, actually building it on the factory floor is another.
The specific measurement is everything. Those twisted pair communication cables have to be manufactured with a twist pitch of exactly 20 to 30 millimeters for high noise immunity. Why does that matter? Well, tightly twisting the wires is literally what cancels out the electromagnetic noise. If a factory machine drifts and leaves a wider gap, that exact segment becomes vulnerable. So manufacturers use automated vision systems to guarantee every single twist falls perfectly inside that tiny 20 to 30 millimeter window.
Then, before any battery pack leaves the factory, automated end-of-line systems verify the terminal impedance is perfectly balanced between 59 and 61 ohms. Remember those two 120 ohm resistors? When you solder two of them in perfect parallel, basic physics says the total resistance must be exactly 60 ohms. By testing for that razor-thin 59 to 61 ohm window, the factory scientifically proves both resistors are flawlessly connected before they ever seal the battery pack.
Finally, we hit Phase 5, DV/P&R, the extreme production validation. This is where they basically torture the system to prove it can survive the real world.
They bombard the battery with aggressive noise, slash its power supply, and push the network to 95% capacity just to prove it still hits its safe state gracefully within 2 seconds. The test protocol here is wild. They strap the car to a dyno, force maximum regen to create massive inverter noise, and then inject even more chaos directly into the lines with a noise generator. They even dropped the system voltage down to just 4.5 volts for 50 milliseconds, simulating a failing 12-volt battery, just to prove the computers won't suddenly black out and crash.
During all these extreme tests, if a daisy chain wire is physically severed, that bidirectional ring topology we talked about adapts and heals the data path in under 50 microseconds, without dropping a single frame of data. Engineers use hardware in the loop rigs to literally sever the connection digitally while the system is running. Once it detects the break, it reroutes the entire COM path backwards and resumes reading data in less than 50 microseconds. That is 1/20,000th of a second. The driver feels absolutely nothing. No warning lights, just perfectly smooth power.
To guarantee absolutely zero invisible reflections or standing waves, the signal's eye diagram must be at least 80% open. This achieves an incredibly strict error rate of 10 to the power of -9. If you haven't seen one, an eye diagram overlays millions of data pulses on an oscilloscope. If the center looks like a wide-open eye, your signal is clean, timing is perfect. If it's blurry or closed, standing waves are trashing your data, and that battery fails the line instantly. Even after 24 straight hours of maximum high-frequency noise injection on the dyno, the acceptable error frame loss rate is absolutely 0%. Not 1%, not 0.1%, 0. The common mode chokes and perfectly twisted cables have to suppress the interference so completely that the network load stays rock solid, ensuring no critical temperature or voltage data is ever masked.
Which leaves us with a pretty fascinating thought to wrap up today's explainer. If the internal self-healing can react in under 50 microseconds, how can software teams evolve the external vehicle networks to be just as indestructible? The internal pack has that instant bidirectional switch fully mastered, but the external CAN bus still relies on those fast and slow reboot strategies when things go wrong. By studying this complete engineering lifecycle we walked through today, maybe the next generation of EV architects will figure out how to make the entire car's network completely bulletproof. Thanks for joining us for today's deep dive, and we'll catch you in the next explainer.